Okay, so the main types of waves we're going to talk about right now are our transverse mechanical waves. Which a specific example would be the wave on a string. So this is my makeshift string, the old school telephone cord. Do you mind holding this end for me? To determine how fast this wave will travel, so right now, the way we're holding it, the wave travels at a certain rate. To change how fast the wave will travel, the only thing we can play around with is tension. So if I pull it tighter, the wave travels faster. Just don't let go. Travels a lot faster. So the tighter it gets, the faster it'll travel. Now granted, if I had different thicknesses, thank you, of telephone cord, then that would also affect the speed of the wave. So the speed of the wave on a string depends upon how tight the string is, so the force of tension, and the linear mass density. So mu, remember, is the ratio of mass per length, so mass over length. So a thicker string will have a greater mass density, and so it will travel slower. The wave would travel slower at the same tension. That's why on stringed instruments, when you tune the instrument, when you're tuning the strings, you're playing around with the tension. You're adjusting the tension until you're getting the pitch you want. Turns out the tension ends up being very, very close for all the strings, especially on, say, a violin or guitar or bass. If the tension wasn't close to the same, there would be a net torque on the neck of the instrument, and you'd bend the neck, and that wouldn't be very useful. So the tension ends up being nearly the same for all the strings, but they have linear mass densities. They have different thicknesses. That means the waves are traveling at different speeds on the strings, which is why we hear different pitches. Okay? The slower the wave travels for that section of string, the lower the pitch will be that we hear. Okay? Another one of the main waves we're going to talk about right now is the longitudinal mechanical waves. Specific example we'll work with is sound. So sound is longitudinal. By the way, what's the difference between transverse and longitudinal?
One
The direction.
is parallel, one is perpendicular.
Right, so it's the direction the medium is oscillating in. Transverse wave, the medium oscillates back and forth as the wave travels down the string. Longitudinal, the medium oscillates parallel to the direction the wave travels. Well, through the medium.
Well, what's a good example in real life of longitudinal?
Sound.
Oh, okay.
Yeah. Sound is a great example. Earthquakes will produce longitudinal that go through the earth, but sound's the most common.
The sound bounces off each molecule rather than vibrating through.
Right, it makes the molecules vibrate back and forth, which in turn makes the next ones vibrate back and forth, and so forth. Right. Now remember, our book doesn't give us an equation for sound. The equation for the speed of sound waves. And that's really because it's kind of complicated. It depends upon the density of the air or the material it's traveling through. It depends upon the bulk modulus. It depends upon the temperature and the humidity, all that good stuff. So basically, we're going to use the value of 343 meters per second unless we're told otherwise. So here's a question for you. If a wave on a string is transverse, how does it create sound, which is longitudinal? Because a stringed instrument, you're hearing sound.
It's the transverse movement is causing the sound to rise in longitude.
Exactly right. So the transverse movement of the string back and forth causes the air molecules to start moving back and so forth until it reaches your ears. Exactly right. The third main type of wave we're going to talk about right now are electromagnetic waves. The electromagnetic waves, light, visible light, is a component of it is a type of electromagnetic wave. It is certainly not the only type of electromagnetic wave. Your book has a table of all the different types. There's gamma rays, there's X-rays, there's ultraviolet, infrared, microwave, radio waves are also electromagnetic waves. The speed of an electromagnetic wave in a vacuum is c. It's 3 times 10 to the 8th meters per second, approximately. It's really like 2.998 times 10 to the 8th, but that's close enough to 3 for our intents and purposes. Now, for each of these, if you change something about the medium, if you change the tension, if you change the temperature, if you change the fact that it's not traveling in a vacuum, if it travels through glass, the speed of the wave will change. Okay? So the speed of the wave does depend upon the medium. If you change anything about the medium, you will have changed the speed of the wave. Okay. So we had our wave equation. To describe the displacement of any piece of the medium of your wave. Now, the reason they write it, your book writes it, is d rather than displacement being x or y, is so that this can work for both transverse and longitudinal waves. D just means how far it was displaced from its equilibrium position. So it doesn't matter if it's displacing perpendicular to the equilibrium position or parallel. So this equation works for both. If you are given an equation with all the numbers except for x and t in there, you should be able to find the speed of that particular wave. You should be able to know that you can pull out the k value, the wave number value, and the omega value. And we know, if we know omega and k, we can find the speed. So the speed of the wave is also equal to wavelength times frequency, or omega over k. So if you know omega and k, you can certainly determine what the speed of the wave is. Questions so far? Another concept. When we talk about how much energy a wave carries, we tend to talk about what's called the intensity of the wave. With light, if you consider light bulbs, say we have a couple lamps, we screw a 60-watt light bulb in one and a 100-watt light bulb in the other. The 100-watt light bulb is going to be brighter. It will be more intense. It would, if that was the only light source in the room, it would make the room lighter than the 60-watt light bulb would. And that's because of its intensity. Intensity is the ratio of power over area. Now power, remember, has units of watts, which is the same thing as a joule over second. So power is the rate at which energy is being created, or really transferred from electrical form to light in the case of a light bulb. Area will have units of meters squared. So intensity has units of watts per meter squared. The area in this equation is the area that the wave spreads out over. So in the case of a light bulb, except for the little bit of the base, the light emits uniformly in all directions. So this area would be the area of a sphere. because the light is emitted radially outwards, other than the base, uniformly. So this area would be the area of the sphere, which is
4/3 pi r cubed.
it's volume,
Oh.
4 pi r squared. So area of a sphere, 4 pi r squared. If we had a laser instead, a laser emits a nice fine beam of light. The area would be the circular area of that beam of light. So just pi r squared. So this area is the area that the light, in the case of a light bulb, the light spreads over. It's the area that the wave spreads over, whatever type of wave it happens to be.
If you had a light bulb and you were shining it on a wall, would you not do the area of a square for that? Because we did one in the homework where it was the sun onto your back.
That's working backwards, yes. So you knew the intensity just on your back. So the area that it's hitting, yes, is what you wanted to use, the area of your back. And that would give you how much energy per second was being absorbed by your back. Okay. If you want to know the overall intensity of the wave, though, you need the overall area that the wave's traveling. Okay. Now, a sound intensity would be related to how loud it is. The sound would be more intense the louder it was, and less intense the quieter it was. It turns out with sound, intensity values it's a huge range. The smallest intensity that people in general can hear, and of course it varies from person to person, we call it the threshold of hearing. So in general, people with normal hearing, the intensity, the smallest intensity a person can hear is 10 to the negative 12th watts per meter squared. It's a very, very tiny number. If things get loud enough, they start to hurt your ears. That point is around 1 watt per meter squared. And sounds can get much louder than that as well. But we have a really, really huge range of intensity values. 10 to the negative 12th all the way up to 1 is a huge range. And to make things a little bit easier, a new scale was invented. It's called the sound intensity level. Sometimes it's just called the sound level. This is your decibel. If you have a stereo, for example, the volume is always listed in decibels. That's the sound level. It's not the actual intensity in terms of watts per meter squared. It's taking your watts per meter squared and converting it into decibels. The equation is actually pretty simple. The decibel scale puts your intensity values on a logarithmic scale, a log base 10. Beta represents the decibel level of that particular sound. So we take 10 decibels and multiply it by the log base 10, not natural log, log base 10, of the ratio of the intensity you're hearing over the threshold of hearing. So the threshold of hearing is considered I naught. So you take your intensity in watts per meter squared of what you are hearing over the 10 to the negative 12, the intensity of the threshold of hearing. In your book, there's a little table that gives you some ideas of different decibel levels.
That your overall decibel is 10, what was that, 10 decibel feet?
That's just part of the equation. 10 dB. dB is your units.
So that's just a constant.
Yeah, that just stays 10 decibels. That's always in the equation. Okay. So I don't remember exact values, but for example, a vacuum cleaner. Vacuum cleaner was around 60 or 70 decibels. So let's say it was 60 decibels. What intensity in watts per meter squared would that correspond to? Well, our equation, theta, this is the sound level in decibels that we're hearing. So 60 decibels goes right there. So 60 decibels is equal to the 10 decibels log base 10 of whatever the intensity is over 10 to the negative 12 watts per meter squared. Now before we can get rid of the log, we need to get the log by itself. So we need to divide both sides by 10 decibels. So 60 decibels divided by 10 decibels will simply be 6. How do we get rid of the log? 10 to the... Let's take both sides. 10 to the 6th is equal to 10 to the log of all that stuff. So 10 to the 6th. 10 to the log cancels each other out, so we get I over 10 to the negative 12 watts per meter squared. It is convenient, getting rid of those logs. So 10 to the 6 times 10 to the negative 12 will be 10 to the negative 6 watts per meter squared. So that's our intensity. So in watts per meter squared, a 60 decibel sound, in this case if it's a vacuum cleaner, is 10 to the negative 6 watts per meter squared. Okay. Now, if you remember just a minute ago, we said the point where your ears start to hurt is at 1 watt per meter squared. If you put in 1 for your intensity, you get out 120 decibels. So let's think about this for a second. Let's say we're on a janitorial crew and there's 3 or 4 of us in a big room vacuuming. Does that mean we're going to end up with 180 to 240 decibels? I've been in a room with a couple vacuums before. It never has hurt my ears. It's never been that intense. It's not valid to simply multiply your decibel level by how many sound makers you've got.
All the sound would have to be in phase,
It's not that it would have to be in phase, it's just how the characteristics of the logarithmic scale in general. So let's say we have 3 vacuum cleaners going. If there's 3 vacuum cleaners, we can multiply this by 3. The actual true intensity in watts per meter squared, that is perfectly valid. If you have 3 vacuums, then you have 3 times 10 to the negative 6 watts per meter squared. So 3 vacuums, the intensity will be 3 times 10 to the negative 6 watts per meter squared. So the actual intensity in watts per meter squared is what you multiply by the number of noisemakers you happen to have. Another side note, 3 times 10 to the negative 6 is not the same thing as 30 to the negative 6. I only say that because I've seen people do that in the past. Multiply the 3 by the 1 and think they're good. It doesn't work that way. So 3 times 10 to the negative 6. If we want to know the decibel level then, we just plug it back through the equation. Put 3 3 times 10 to the negative 6 watts per meter squared in. I naught's always 10 to the negative 12 watts per meter squared. That takes us up to 65 decibels. Not a huge change in terms of the sound intensity level. So, only takes us from 60 to 65. So intensity, to not confuse the two. If you just see intensity in and of itself, not intensity level, that means I in watts per meter squared. If you see sound intensity level, that word level refers to the decibel scale specifically. Okay. Really easy to convert back and forth. If you're given decibels, you can find the intensity. If you're given intensity, you can find the decibels. The biggest thing to keep in mind is if you have multiple things making noise, that you have to find their intensities in watts per meter squared and combine them prior to running them through this equation.